take some time to do one or so that you may have a question about. I thought I'd just pick one out of the section on like 9 through 41i. Now, the other class we did number 31, that does have kind of some simplifying in it that you have to talk about, so I thought maybe that'd be good. Would that be an okay one to do, 31? Okay. And then, so let's look at 11, then we can look at 31, and then we'll jump into like 43 in that section in there. Okay? And so if there's any others in that 9 through 41, maybe we can quickly talk about it. But so anyway, what we're looking at here is, now in these first few, this is not something you're going to have to do ever again probably with derivatives, but what we wanted to do here is show that when we do the product rule, we get the same thing as if maybe we'd have just simplified it first. But many times we don't have that option. If I have x times sine x, there's nothing to simplify. I have to do the product rule. But on some of these, we kind of have an option. So I could do the product rule on this one. So the product rule says derivative of the first, bring the 1/2 down in front, drop that to negative 1/2, leave the x to the 1/3 alone, plus leave the x to the 1/2 alone, and then derivative of x to the 1/3, which would be 1/3 x to the negative 2/3. Now, obviously, these started out as radicals, but you have to be able to write them as powers to be able to do those derivatives. Now, remember, our product rule, of course, was u prime v plus uv prime, right? That's our derivative. Now, here's the algebra we have to be able to do. I mean, there is no getting around that on the Gateway test, when we do derivatives, you have to be able to do some algebra. That's just part of it. You're not going to have to do that on every one of them on the Gateway test, but there's going to be some where there is some simplifying to do. And so on one like this, although we wouldn't have one quite like this, but we'll do with number 31 as an example. We can multiply this together and we can add these powers. Now, negative 1/2, that'd be negative 3/6, plus 1/3, that'd be 2/6. That adds to negative 1/6. So this would be 1/2 x to the negative 1/6. Here, we would have 1/3, and then here we can add those powers. That would be 1/2, which is 3/6, plus negative 2/3, which is negative 4/6. 3/6 take away 4/6 is negative 1/6. And that's nice, because when the x's have the same power, what can we do? What's x squared plus x squared? 2x squared. When they have the same power, they're like terms. We add them together. So we can add these two together. So 1/2 plus 1/3, well, 1/2 is 3/6 plus 2/6. That would be 5/6 x to the negative 1/6. And that would be our derivative right there by the product rule. Now, it turns out that this is a problem that we would not need to do the product rule on. We could simplify it first. Now, notice my notation. This is so critical because I already know on this last quiz that there were some people might have missed some points because of their notation, right? This is the h function. When I do the product rule, I've done the derivative, and so that is the h prime function. But when I just add these powers together here, which is what I'm going to do when I simplify this, I have not done a derivative. So when I add the powers together here and get x to the 5/6, that's the h function. And I should label it so. You need to label your functions, and you need to properly label them, or you lose points because you've got to communicate correct mathematics. So here I've done the derivative, that's h prime. Here I've just simplified h. Now I'm going to do the derivative by the power rule. So I bring the 5/6 down in front, drop the power by 1, and I have this, and sure enough, I get the same answer as before. So that's what that section was about. Okay? All right. If you have some other questions, let's go to 31 then. If you have some other questions in there, maybe, it might be a situation where you come and talk to me individually, especially things about some algebra kinds of things. Okay? So let's look at 31. 31 says what? Is it f of x? F of x equals, help me out, x plus 1 quantity squared over x squared plus 1. So this is a quotient rule. Now, we could possibly FOIL out that top. And if you did, that's fine. Your answer will look a little different than mine here in the beginning. But eventually you should end up getting down to the same place or something similar to what I have at the end. Now get your calculators out because we're going to do something here with them in a second. But I would suggest not foiling that out. All right? Because if that was a third power, a fourth power, a fifth power, we certainly wouldn't want to foil it all out. Okay? So I would suggest when we have one like that to not foil that out most of the time. It usually leads you down a road that is probably not the best way to get there. Okay? It's not wrong, and you might be able to get there that way, but it might not be the best path. So we're going to do the quotient rule, which says u prime v minus uv prime all over v squared. So the derivative, I'm going to label that f prime. I really think you ought to get in a habit of writing this out instead of just randomly writing work down. Okay, because when it comes to other quizzes and tests that we have, right, this is important. So we do the derivative of the top, which means we bring the 2 down in front. We leave the x plus 1 alone to the first power, which I won't even write. And then do we have to kick out anything? No, there's nothing in front of the x, so we don't have to kick out anything. Then we're going to leave the bottom alone. So we're going to multiply by that, and it is multiply. So we need parentheses around it. Very important that you put parentheses around that. Whenever you have plus and minus signs in a thing, and you're multiplying it or whatever, you've got to put parentheses. Okay? Minus, now we're on to the uv prime part. So the top left alone times the derivative of the bottom, which I would put 2x. I would put that in parentheses, although as it turns out you don't need it, but it's better to have parentheses if you don't need them than to not have them when you need them. And then it's all over the bottom square. Now, one thing I will caution is sometimes in the product rule when people are doing, or the quotient rule, when people get so caught up doing the top part, then they forget about the bottom part, okay, the v squared part. All right, now, here's what I wanted to talk about. On the gateway test, that's not good enough, okay? We need to simplify. Now, talked yesterday about simplifying. I said just merely rearranging things is not important, but I did talk about factoring if you could cancel. Well, the quotient rule is a prime time that some canceling could occur because you have a top and a bottom and you might need to do some things. Now, there's going to be some times with the quotient rule that it just doesn't simplify. Usually when you mix a bunch of different function families, like you have some e's with some signs or something like that, it's very possible that nothing's going to cancel. And so then you don't need to factor if things aren't going to cancel. We talked about that yesterday. But here, since I got a bunch of x's and stuff, I think maybe some things might combine or cancel or something good could happen. Okay, they may not cancel, but I might be able to combine some things up there on the top. Now, I would first think of factoring rather than multiplying. Like right here, you could say, well, I could foil this. And to me, that would work, but there's actually a better way. When you do the quotient rule, you've got this piece minus this piece. That's where you want to think about factoring. You want to think about factoring something out of those two red pieces. Okay? And so for my money here, I would be looking at this, and I would be looking at this and seeing if there's anything I can factor out of it. What do you notice? A 2 and an x plus 1, right? And that's what I'm going to do. So I'm going to take a 2 and an x plus 1. Now, it's possible sometimes that you do this and it leads to a dead end, and that's fine. If it leads to a dead end, you go back up and you just circle this, and you take that as your answer, okay? But I would go down this road and I would try. So now I'm going to put square brackets, parentheses would be fine, but I'm going to have a bunch of stuff left, so a lot of times we use that. Doesn't matter, parentheses would be okay. So if I take out a 2 and an x plus 1, that's going to leave me an x squared plus 1. Don't really need parentheses there because it's not going to times anything, so that's fine. Then I got my minus sign, and what do I have left here? An x plus 1 and an x. So an x and an x plus 1, right? Now that's going to be, well, let's just rewrite. And then don't forget we got the whole bottom square. All right, now that's going to be something kind of nice, I think. I'm going to have this factored out. And then in my brackets, this is going to be what? Minus x squared minus x, right? When I distribute that negative x through there. And so what's going to happen? X squared minus x squared is going to drop out. So that alone was worth doing it right there. Okay? And what do I have left? I have a 1 minus x right there. All over an x squared plus 1 quantity squared. Now, I was hoping something would cancel, but it turns out it doesn't. Right? The x plus 1 can't cancel with anything down there, and there's nothing I can do. But that is definitely simpler than that thing in blue that I have up there. Okay? So the question was asking the other class is, would I have to do that on the gateway test? And I would say yes. Now, you're not going to have to do 10 of those, right, on the gateway test. This isn't an algebra test, but algebra is important. So I don't think you would have more than half of them that you would need to do very much algebra. And maybe only one or so that would have that much algebra. You see what I mean? I think it's important that we able to do it. Because think about what we're going to do with this. I mean, when we go on to number 43 and 44 in that section here, we've got to be able to combine this ability to do derivatives with doing the chart and all this stuff we learned in chapter 1 and 2, local max, local min. That's what chapter 4 is actually, right? Think about what we're doing. In chapter 1 and 2, we learned about derivatives, learned the chart, learned what we can do with derivatives, local max, min, learned it graphically, learned it with equations, learned about how we can find all these things in the chart and those kind of things with derivatives. And now chapter 3 is kind of taking a pause and saying, you know what, if we need to be able to do derivatives to be able to do these things, we better learn how to do derivatives of any kind of equation. So we know all the different basic derivatives, or we've written down. Tomorrow I'm going to give you a bigger list of all these rules. Now, yesterday we learned about what if we multiply and divide functions. And today we're going to talk about what happens if a function's inside of another function. And that gives us all these different combinations of functions that we need to be able to do. And so now that we can do those derivatives, and so the idea would be now that we can do those derivatives of any kind of function, now let's go back and let's talk again about local max, local min, chart stuff with all these types of derivatives. So that's what chapter 4 is going to do. Okay? So our focus right now is the gateway test. And our focus is being able to do these problems like this. Because this is what the gateway test is like right here. But we're also going to, as we go along, practice the other stuff, the chart, the local max, min, those kind of things, because that's what we want to be able to do with these derivatives. So if I'm doing a derivative and setting it equal to 0, like say I was doing that with this derivative, I would want to simplify that as best I could if I had to then set this equal to 0 and solve it. Okay? So we need that skill. We need to be able to do that. All right, now, I want to show you, get your calculator out. I want to show you now how you can use your calculator to check your answers. Yeah. I'm going to show you how you can check your answers on your calculator when you're doing and practicing these. Because, yeah, this is number 31. You can look it up in the back. I don't know. Did anybody look? Is that how the back wrote it? They multiplied these together? Yeah. So they may have multiplied all that together and whatever. See, and that'd be fine. But to me, that's just kind of rearranging, right? I would say leave it in that factored form. That's okay. Right? And don't get too hung up on, well, let's see, did he say I could do this or do I factor it? Okay, I'm trying to give you some broad, general rules. Rearranging I don't really care about, just moving things around. But if you can move things around and put them together, then you should do that, like what happened there. Okay, we factored out, we were able to cancel some x squared, whatever, simplified it down. Okay, so we're looking to do those kind of things. So, and you'll see the more we do them, the more you'll understand what's happening. But people sometimes do as much damage trying to simplify too much than not simplifying enough. I mean, they'll take problems that they're perfectly done with, there's really nothing else that can be done, and they try doing crazy algebra to it because you think you get hung up on every problem that has all this algebra. Okay, and it doesn't. All right, so here's how you can check on your calculator. So you've just got done working this problem. Let's have the calculator do the derivative. So go to that template by the 9, right, the key that gets the derivative command, and type in this original problem. Have it do the derivative of that original problem right there. Make sure you get the parentheses in the right place and the squares and everything. But here's, even though the back of the book has the odd answers, and that'll be fine, and the website, sometimes you can type in your answers and check them. But this is a good way when you're working problems where you can check to see how your answer is. Now, it's not going to tell you if you've simplified it enough, right? Because you might just have stopped at this blue thing, and you might check that, and the calculator would tell you you're right. So this isn't perfect. This isn't going to tell you that, yes, I've simplified it down, but it's at least going to tell you if you did the rule right. All right, so does it look like this? Pretty close, right? But it takes a negative out. Here's why. Because the calculator doesn't like the 1 minus x. It wants to write it x minus 1, right? So they take a negative out, and they make that an x minus 1, right? But otherwise, it's the same, right? So now you probably could tell. If you type that into your calculator and you had this on your paper, you could probably tell that's what happened. You could probably tell the negative came out and whatever. But let's say you could. And so you're wondering if yours is right. So here's what I want you to do. I want you to type yours in. So, or this one. Everybody type this one in right here. So go to a new line and type this in right here. All right, and once you get that typed in, don't need to hit enter or anything. Now, here's what I used to tell people, but I found something I think works better. What I used to tell people is type this in. Don't do it right now, but you type this in and hit enter. And what I thought would probably happen most of the time is the calculator would simplify that one the same way it simplified the other one, and then you would see if they match. What I found is it didn't always do that. It didn't always simplify in the same way 2 times in a row, which is weird. But that's because we typed something different in. So I decided to try this. So you type this in, and then hit, at the end of it, hit equals, and then arrow up and grab the one you have the calculator do. And hit enter, and then, right, it'll paste it in, then hit enter, and what do you get? It should say true, right? And I thought that was a better way, because now what it's saying is those two are equal. If you get false, then you know something's wrong, or maybe you typed it in wrong, but you know something was wrong with your derivative. So that at least tells you that your answer is the same as the derivative. You just didn't simplify it the same as what they did, but that doesn't mean the way the calculator did it is not necessarily the perfect way to simplify it. I wouldn't expect you to take out that negative, for example. But it can be helpful to tell you if you're on the right track. About the only way to know for sure if you've simplified it right is the things we talk about in here, and is if you come in and ask me problem, right? But again, we're going to talk a lot about the simplifying because people struggle with that, but don't think that they all are going to have that in. Okay? All right. So, any other questions on that up through like 41? Because I want to go on to 43 and talk about that. What's 23? Like this? Right? So I would rewrite that as x to the 1/2 times natural log of x. And so now the derivative, notice how both of those I called f of x. Now the product rule would say do the derivative of the first times the ln x left alone plus the x to the 1/2 left alone times the derivative of ln x, which is 1 over x. Now, I would say to you, this is a great example then of one that's got a little bit of algebra, but not very much algebra. Right here, to me, you can simplify that. Because that's x to the 1/2 times x to the negative 1, right? Where you just add those powers, and that's what? What do you get when you multiply that together right there? X to the negative 1/2. Or you could think of canceling. You could think x 1/2 of x. You could subtract the powers. 1/2 take away 1, right? Is negative 1/2. Or it's 1 over x to the 1/2. I don't care. You could leave that any of those ways. But I think that should be simplified. Those two should be put together and multiplied. Now, at this point, I would stop. I think you're done. Now, you might say, wait, there's an x to the negative 1/2 in both of those. I could factor it out, right? But why factor it? Because we hold 1/2. We could cancel. Or maybe we could put some things together. But if I take out an x to the negative 1/2, that'd be fine. You could do it. It just wouldn't be necessary. So that's a better example than 31 from the sense 31 would be on the hard end of the simplifying. That's a lot to do. That factor out But you might have one of those. Now, if that's the only one you missed, you're good, right? Maybe there'd be 2 at most, but I don't think there'd be that many. But there could be a couple in there that have a little bit of simplifying, like that. Okay, to me, that's a little bit of simplifying right there. Okay? All right, yeah, but if you took these x to the negative 1/2 and put those on the bottom, took them back to square roots if you wanted to, you could do that. You know, that'll be fine, but it's not necessary. Okay? Now, if we were doing a derivative setting it equals 0 and wanting to solve it, yeah, then all of a sudden we start talking about wanting to factor things and start doing some things there, right? And we'll get into that in chapter 4, but right now, right, you could stop. All right. What I'd like to do now is go on to number 43 here and talk about that section a little bit. This section really makes you think about your rules. It also does a nice job of making us think about increase and decrease and all the chart components and those kind of things. So I want to run through some of this. Probably if you didn't write a lot of this down, it's going to be hard for you to write it all down now. But this is what I was looking for as I came around. Now, some of you on this section didn't have a lot down, or you just had some answers down, and you'll find out as we go through this, there's a lot of stuff should have been written down. Okay? But first of all, let's just talk about what's going on. Some people were confused because you had this F graph, but then it kept talking about H and M. Well, here's the H function right here. It's got F in it, okay? Now, that's not going to be on the gateway test at all, but this is the part where we're thinking about, putting this together with what we learned in chapters 1 and 2. So they want us to find H prime of 2 and H prime of 4. Well, here's the thing. You've heard me say it before, and it's very important. Before you can find H prime of 2, you need H prime of x, right? So what we need to do is write down H prime of x. Well, there's H prime of x. We need the product here. So derivative of x squared is 2x. Leave the f of x alone. And then switch it. Leave the x squared alone. Do the derivative of f of x is f prime. Well, that's H prime of x. So therefore, H prime of 2 is simply a 2 plugged in everywhere the x is. Now, again, I emphasize, I think writing this out is very important. I think it helps you know what to do if you write this stuff out using the proper notation. So once I put the 2's in there, it becomes pretty evident. 2 times 2 is 4. F of 2 means look at the F graph at 2 and see the y value, and I think it's negative 4. 2 squared is 4. And look at the F graph at 2 and look at the slope. Well, what's the slope? Turns out it's right at a minimum there, which is 0. So we get negative 16 plus 0, and the answer is negative 16. And that's it. Now it said estimate, but it turns out that's exact because we didn't have to estimate the slope. We could tell it was 0. And then they wanted H prime of 4. So we just take our H prime of x again, and we just put 4's everywhere. Right? We just put 4's everywhere. 4 times 4 is 16. F of 4 actually is 0, crosses the x-axis there, so that whole thing turns to 0. 4 squared is 16, and the slope at 4, now the other class we came up with 4. Seemed reasonable. You might have got something a little different than that, okay, which is okay. I mean, it said estimate, right? It said estimate. So 16 times 4 is 64, but you might have been off a little bit, depending what your slope was, but it has to be in the ballpark. All right, so that's 43. Now, 44 said, remind me, what did 44 say? Oh, show that H has a stationary point at x equals 0. So what are you going to do there? Just put a 0 into H prime, and a stationary point means you better get what out? You better get 0 out, right? That's what a stationary point is when the derivative, the output is 0. So we put a 0 in. Well, sure enough, you put a 0 there, you're going to get 0. Put a 0 there, you're going to get 0. So when you put a 0 in, you get out a 0 in H prime. That is a stationary point. That's all you have to do. But show it, right? 45. Now, 45 was an interesting one. 45 said, is H concave up at negative 0.5? Well, now think of the chart. When is H concave up? Double prime is positive. Now, in the other class, somebody said when H prime is increasing. That's true when H prime is increasing. The problem is you can't look at an equation and tell when an equation is increasing, right? You can only tell when an equation has a certain value, a positive or a negative or 0 or whatever. So the only way we can do when H is concave up is see if H double prime is positive. So we need H double prime. So here's H prime. We need H double prime of X. Then we can plug in a negative 0.5. Well, good God, how are we going to do H double prime? Two separate product rules. Yeah. And we're going to run into that. As we go through this week, we learn these rules. You're going to have combinations of different rules in the same problem. So to do this derivative, you've got to do a product rule. And we also have the rule that says when you're adding functions, you just do their individual derivatives. So we do this one, which is a product rule, plus this one, which is also a product rule. So it ends up being this right here. Right? Do the derivative of 2x, which is 2. Leave the f of x alone. Leave the 2x alone. Oh, and by the way, the 2. This came up in your class. How come I put the 2 with the x? Why not 2 times x times f of x? Well, sure, I could do that, but then it's harder. Then I got 3 things multiplied. It's okay to just group the 2. Anytime you have a constant like that, just group it with one of the functions and treat that as one function. So the 2x I'm treating as one function. You'll see as we go through this how that is helpful in doing these. So I'm grouping this as that's my u and that's my v right there. All right, so anyway, the 2x, leave it alone, f prime, blah, 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 we go through this. All right, now, we want to know at negative 0.5. Excuse me. So at negative 0.5, we're going to plug that in for x. So I went through, I wrote it all out. Even though I'm not being graded, I thought, you know, what the heck. But then again, I didn't have anything to do for 2 hours during map testing, so that was a good practice for me. But wrote this all out. F of negative 0.5, we can just read that right off of the graph, and we decided it was 2.5. Now some people might have thought it was 2. It's right in that ballpark. It's somewhere around 2, 2.5, something like that. Okay, now you say, well, it's going to make a difference. Well, I don't know. It might. What are we looking for here? We want to know if H double prime is positive or negative. That's all we need to know. Is it positive or negative? So this might make a difference, might not, but we called it 2.5. All right. And then we had to take 2 times negative 0.5. That's negative 1. And then we need f prime in negative 0.5. So we need the slope there. Well, it's definitely negative, right? So you look at the slope at negative 0.5, and we came up with negative 4 is what we thought it was. Looked like you go over 1, down about 4. But the key is, look what you got. You got a negative times a negative. See, that's what's going to be the key. I don't think it's going to be what the number is as much. And then I didn't fill this in here because it's the same. Notice this one is the same as this one. They're the same. So I just, when I did one, I would have the other one. So that's going to be a negative 1 times negative 4 again. Okay, so that's what that is. And then we get here. Negative 0.5 squared would be 0.25. Now what about this? Well, this is a question we were just talking about here at lunch. How do I tell f double prime from f? Well, yeah, but I mean, think about the chart. What things on f have something in the f double prime line? Concave up, positive. Concave down, negative. Possible inflection point, 0. Those are the only 3 things that compare f and f double prime. So look at the f graph at negative 0.5, and which one of these 3 do you see? You see concave up. It's basically a parabola. So at negative 0.5, you can tell that f is concave up. Therefore, f double prime is positive. That's all we know. We don't know what its number is, but we know that it's positive. And it turns out that's all we need to know. Okay, because look what you get. You get 5 times positive 4, or excuse me, plus positive 4, plus positive 4, plus we don't really know, but you know what? We do know it's positive. And so all we cared about, remember, is are we going to get out a positive answer for H double prime? And we certainly are, because every one of those turned out to be positive. So since H double prime is positive, don't forget what we were asking. Since H double prime is positive, H is concave up. H is concave up. So that was a lot to do there. Okay, but it's good practice on the product rule. We did some graph stuff. There was a lot of different things we reviewed there, and we're able to work through. Okay, 46 and 47 then just ask some more of those same kind of questions with H, and then it gets into M. You had to find M prime of this or M prime of that. And I want to talk about 48. Okay, so on 48, so we've got m, and they ask, is m increasing at 3? Well, if m's increasing, what do you need? M prime to be positive at 3. So that's the question, is m prime positive? So this is very much like we just got to do at 45. We need to know if m prime is positive at 3. So before I can get m prime of 3, I need m prime of x. So there is my quotient rule derivative. Right? This is a quotient rule. Right? So, derivative of the top, f prime. Bottom left alone, got to have parentheses around. Minus, top left alone, derivative of the bottom. Now, it turns out those don't need parentheses, but I put them there, again, better to have them and not need them than the other way around. And then the bottom squared is there. That's m prime of x. Now I need m prime of 3. So I'm going to put a 3 in every one of those x's. So in the other class, we did the slope at 3, or this morning actually, it was before school, but the slope at 3, we thought it was about 2 on the f graph. This turns out to be 10. F of 3 looks like it's negative 3 on the f graph. 2 times 3 is 6. So we get 20 plus 18, because that turned to positive. 20 plus 18, the bottom is 10 squared, which is 100. So we end up getting 20 plus 18 over 100, definitely a positive value. So since m prime is positive at 3, m is increased. Okay? So there you go. $79. All right, so on 79, we're given this function. Now this is where it all kind of comes full circle. This is where we tie it all in with what we were doing back in chapter 2 and chapter 1 with max min. They happen to choose a global max min problem here. Now, oh, by the way, before I do this one, I meant to say this and I forgot. I've mentioned it to several people who came in. Number 19. Had 1 minus x cubed, and it had 1 minus x on the bottom, right? And you were supposed to do it 2 ways, right? One was the quotient rule, which would be easy to do, right? Quotient rule. And then one was you were supposed to simplify it first. Well, I'm guessing many of you didn't know how to simplify. In Algebra 2, there was a rule for factoring in difference of cubes. It was a minus b times a squared plus ab plus b squared. That's what the rule was. So I don't expect you to memorize that. I can't think of a time on the repeat test anybody ever needed to know that. So this would factor in 1 minus x, and then would factor into 1 plus x squared over 1 minus x, and those would cancel. And that's what they were talking about. So I apologize if you spent a ton of time trying to factor that one, but I suppose you could have Googled it. Right? Could you just Google that anyway? But, all right. So, back to this one. All right, so we've got, we're supposed to find the global max min. Now, I'm not going to get into inflection point. That would be a second derivative. You'd have to do that again and so forth. I mean, it's very much the same idea. And that's something we'll be doing a lot more when we get into chapter 4 and so forth. And as we review for our midterm and those kind of things, we'll do more of these. But let's just focus on the max min, one derivative. So this clearly is a product rule. Now, they only limit us from 0 to pi. It's a global max min. It asks what's the max value of the function, what's the max or the min value of the function. That's a global max question. Okay? So we do our list of candidates. So we're going to check the derivative, or excuse me, check the original at the endpoints and wherever the derivative is 0, the stationary point. So I'm going to put 0 back into the original, and I'm going to put pi back into the original. Those are my endpoints. And I need to find when the derivative is 0. So I did the derivative. Now let me make a comment here about this derivative. All right, so when we do the derivative, we're going to do the derivative of e to the x, which is e to the x, leave the cosine alone, plus we're going to leave the e to the x alone, times the derivative of cosine. Now, what's the derivative of cosine? Now, I see people doing this all the time. What's wrong with that? That means subtract. That doesn't mean times a negative cosine. Now, sometimes people put a dot in there. Now, technically, that's okay, but it's just not a good way to write it. If I told you to write x times negative 3, I don't think you would write it like that. If I said write down x times negative 3, my guess is you write negative 3x, right? You put the negative 3 around on the other side, okay? And so I think we should do the same thing here. I think we should take that negative and put it out in front. All right, I think it's going to be way less confusing. And that's one that happens all the time with cosine, because the derivative of cosine is negative sine, and whenever we're tacking that on, or doing that in a product or quotient rule, we write it this way a lot, and that gets confusing. So I think that ought to go around here, okay? Just to eliminate that kind of confusion. All right, and then we're going to set that equal to 0. Some of you on the quiz forgot when you were doing your derivative and solving it for maxims, you got to put the equation in. You got to set it equal to 0. That's key. All right, now, whenever we're solving one of these, this is the first time we've run into one of these. We practiced some of this on that worksheet I gave you. Well, this is one of those like was on there. I would take out an e to the x here. All right, let's take out an e to the x, and we end up with this. Now, whenever things are multiplied between 0, one of them has to be 0. So, either e to the x is 0, or cosine minus sine is 0. Now, when is e to the x 0? Never. Never, never, never. There's nothing you can put into there as a power and get out 0. It's never going to happen. So that's never. Here I would add sine x over to the other side. Now, I have had people that want to divide now, both sides by like cosine or something, and you get tangent equals 1, but that's bad. Anytime you divide by an x, you've eliminated possible solutions. If you divide by an x, you can't divide by 0. So anytime the thing you divide by is 0, you've lost that as a possible solution. So you do not want to divide by x's if you can help it. Okay, so I would stop right there. Well, when does cosine equal sine? Yeah, think of the unit circle. The only time that happens is pi fourths. They're both root 2 over 2. Now, it also happens in the third quadrant when they're both negative root 2 over 2. So it would also happen at 5 pi fourths. But what's wrong with that? It's outside of our interval. Our interval is only from 0 to pi. So we are not going to consider that one. So there is where the derivative is 0. So that has to go into our list of candidates. So we need to plug that into our original function f. Now at this point I'm going to stop on this one, because here I would let you probably use a calculator or I wouldn't give you one of this as a global max min. If you had your calculator, you could have used that to solve, right, which would have been nice. But what's going to happen here is when you plug these values in, you're going to get some weird kind of messy stuff. Now, later on, when this is really important to us for doing this, right now our focus is the gateway test and doing derivatives. But when we're more focused on this for like the midterm and stuff like that, I'll show you how we can do a number line to help us with our global max min. Okay, what we're going to find out is we can tell that at 0, this graph starts at a certain place, then it increases for a while, then it decreases for a while, and then we can tell where our max is going to be in our min and so forth. Okay, even if we don't know their exact values because we can't use our calculator. So I'm just going to stop there, but we would plug those into f, and we would do that and get our max. All right, but I wanted you to see the product rule, and I wanted you to see then the factoring and how you could do it. All right, so let's move on. Let's get your notes out. Let's get your calculators out. Well, you got your calculators out, I think, already. So let's talk about the new rule that we have to do today. We said we were going to talk about what happens when a function goes inside of another function. And this is probably the most important of all the rules. And just because it's used all the time It's the one you're going to be thinking about the most. Because most problems have something inside of another function. Most functions aren't just e to the x. Most functions aren't just x squared. Most functions aren't just sine x. They have other stuff inside. Now, before we do this, I would say to you that we've kind of done this already, right? If I have sine 3x, the derivative is 3 sine, oh, whoops, yeah, not sine. 3 cosine 3x. Now remember why we did that. We did that because the 3 is squeezing that graph horizontally, which we said would make the slopes what? Steeper by a factor of 3. It would also squeeze in where they happen. So we said we had to leave the 3x on the inside because the derivative had to be squeezed also. But we said they would be 3 times as big a value, so we had to tack on or kick out that 3. So we've been doing that and saying anytime we have an x inside the function, if there's a number in front of it, we have to kick that number out. So we've been doing that for a while. But that's the only kind of function we've put on the inside so far, is an x with a number in front of it. We've never done something like this. So I want you to have your calculator do it. Go ahead and have your calculator do this one, and let's see what we do. Is that what we're getting? So what do you think? The thing we're kicking out is the derivative of the inside. But notice, everything we did before is the same. We leave the inside alone. The inside stays the same. And isn't that really what was happening over here too? What's the derivative of 3x? 3, right? The number in front of the x was a 3. Now, I knew that when I told you that before, right? Why didn't I tell you that's what we were doing? Well, it didn't matter, number one. And number two, I wanted you to realize that the reason we were kicking out that 3 was because what it was doing to the slopes. I wanted you to have that connection, okay? But now we see it was just a special case of a more general rule, okay? And that is what we do when a function's on the inside. So we're going to talk about that, and we're going to write it out in words and write it as a rule. But basically, it's what we've been saying. You do the derivative of this part, what we're going to call the outer function. You leave the inner function alone, and you kick out or multiply. We better just instead of kick out, we better say multiply, because I noticed a few people on the quiz were adding on the 3 or whatever instead of multiplying the 3. We multiply by the derivative of what's on the inside. So it's kind of a 3-step process. Derivative of the outside, leave the inside alone, and then kick out and multiply by the derivative of the inside. So that's what we got. So let's write it down 2 ways. Let's write it down as a rule, and let's write it down maybe in words. I don't care if you write it down in words, but the rule we definitely want to have down. And here we're not going to use u and v because we actually have to put a function inside of a function, so our f and g of x notation works better, actually. All right, so we got the derivative of f of g of x. We have an outer, and then we're going to talk a lot about this over the next day, is the outer function and the inner function. Which is which? Sometimes it's easy to tell, sometimes it's not as easy to tell. So what do? We do the derivative of the outer function, so that's the f. So the derivative of f is f prime. We leave the inside alone, that's the g of x. And then we multiply by the derivative of the inside, which would be g prime. So that's what the chain rule looks like in math notation. And then this is what it would be in words. We do the derivative of the outside function, we leave the inside function alone, and then we multiply by the derivative of the inside function. Now this really gets interesting when you have something inside of something and then that's inside of something else. Or The inside function is a product. So when you do the derivative of the inside function, you have to do a product rule. You see what I mean? So these things can kind of be combined together. And we'll do, with the time we have left here, we'll do some examples. Okay? All right, now, just, you don't need to write this down, but just let me give you one quick word about composite functions, because that's what this is called. When I write f of g of x, that's called a composite function. Or you could do this, g of f of x. Now, those are two different functions, right? You put different one inside, those are different. Okay? Your book also uses some weird notation. I call it the fog notation, because it looks like this. I don't know, for some reason, to me, that spells fog. But they'll do that. That means f of g of x as well. So if you see that in the book problems, that's what they're talking about, f of g of x. Okay. But if I told you that, so you're going to have a few of your first homework problems are going to ask you to do this kind of stuff. So they're going to tell you f is x squared and g is sine x. All right? They're going to tell you what f and g are, and then they're going to want you to do f of g of x. Well, what would f of g of x be? Okay, now, it's interesting how you said that. Yes. And Allie, you said sine of x squared. Now, when I hear that, I don't know what that means. I mean, is that what you mean? Or do you mean this, right? You said sine squared x. Or do you mean this? Or is that different than this, right? The parentheses are going to make a huge deal here, right? I've talked a lot about parentheses. You can't be a math teacher without talking a lot about parentheses. It's really important. So yes, that means you put sine into x squared. So it's going to be this, sine of x squared. Now, is that the same as sine squared x? Yes, those are the same. Now, this is that notation I'm not fond of. I use it myself, but we got to remember what it really means. It means, and talk about the outside function. When you look at sine squared, you got to understand that squared is the outer function. The sine is on the inside. Now, what's g of f of x in? Now, you hear how you guys are saying the same exact thing for both of those? Somebody could read this sine of x squared, and the one you're telling me, I think, right now is this, right? Now, those are two different things. But if you just say sine of x squared, they sound like the same thing, right? So the first one I would say is sine of x quantity squared, or sine squared x. And the next one is sine of the quantity x squared. Those are different things. Okay, so be careful about that. Luckily, none of our tests are oral quizzes, so you're not going to have to talk about it. But, right, understand the difference. All right, so let's try that one. Let's try that one right here. I'm going to start writing my answer up on the board, so if you don't want to see it, look. Now, we've been doing things similar to this, right? I mean, we've had the parentheses, then a power. The outer function is clearly the 8th power. Now, if I ask you what's the outer function, how would you answer that? If I said, what's the outer function, what would you say? What's something to the 8th power, right? Or if you said x to the 8th, that would not be wrong, right? What's the outer function? It's x to the 8th power. Or what you'll hear me say a lot in the next coming days is something to the 8th power. That's the outer function. Something to the 8th power, okay? And the way you do a derivative of the 8th power, something to the 8th power, is you bring the 8 down in front, drop it to a 7. You leave the inside alone, so that's what I've done so far. And then we do the derivative of the inside. Now, notice what I did there. I wrote down the first two parts, derivative of the outside, leave the inside alone, and then I just put a big set of parentheses because that's the part we always forget. Okay? And so now I'm going to do the derivative of the inside. So what is the derivative of e to the 2x? Oh, I kind of threw a curve right off the bat, didn't I? I gave you the inside function had something inside of it even, right? But hopefully we've been so used to that one that you don't even have to think of that as a chain rule. I think you just look at that and you say, oh yeah, I'm going to kick that 2 out. And that's the best way to think about it. And that's why I like the fact we've already been doing those, because we don't have to think about it as a chain rule. So yes, that's 2e to the 2x plus derivative of 3x is 3. So we got a plus there, so we do each individual derivative like that. There's our answer. Now, the reason I put the parentheses there first is because, again, I'm going to say this over and over, so hopefully nobody does it. But what I see people do is they go, okay, I'm bringing the 8 down in front. I'm going to leave the inside alone. I'm going to drop that to a 7. Then I'm going to times by the derivative of the inside. So I put my times, and then I do the derivative of the inside and leave. What's wrong with it? You're just, the add 3 is not included. The plus 3 is tacked on at the end. You got to multiply by that whole thing, and I don't care how big you make this dot, it does not make that include all this. It just doesn't. Okay? You've got to have those parentheses. Have to. Okay? All right. That's it. Now, remember we were talking earlier about how on a lot of these problems you won't have to do a bunch of simplifying? This is all you need to do. Now, could you take this 8 and distribute it through into there? Sure, but that doesn't help anything combine, or it doesn't help anything eliminate or cancel. So I wouldn't do it. Now, if there was a 4 sticking out here at the end, yeah, that 4 and that 8 ought to go together to make a 32. But there's no reason to distribute that 8 through there. So you're done. So some of them on the gateway test are going to be like that. You just do it, follow the rule, you're done. All right, let's don't do this one. This is just another power on the outside, so we have to think too much about that. Let's do this one. Okay, we got about 5-6 minutes left here. So let's try this one. Now, what is the inner function? The inner function. Sine x is the inside function. The outside function is 2 to the x, or 2 to the something, right? So we start by doing the derivative of the outside. So we should be starting with the 2 to the x derivative rule. That's what we should be thinking of. Okay? And just for time's sake, we'll just kind of go together. If you know it, you've probably done already. We should be thinking of this derivative rule to start, because that's the outer function. And so what is this derivative rule? Keep it the same and multiply by natural log of 2. Now in the quiz we had some people think we're going to bring the x down and do x minus 1. No, 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 that's not. That's when you have x raised to a power, right? When x is raised to a number, you have that. When you have a number raised to an x, that is an exponential function. So the rule for 2 to the x is 2 to the ln 2. But we don't have 2 to the x, we have 2 to the sine x. That's the inside. Well, in the chain rule, it says keep the inside the same, right? So what am I going to write here? 2 to the sine x times ln 2, because I'm just following the rule now, right? So what have I done so far? I've done the derivative of the outer function, the 2 to the power function, which told me to tack on an ln 2. I've left the inside alone, and now I'm doing the derivative of the inside. Derivative of sine is cosine x. Now, I don't need any parentheses here because there's no plus signs anywhere. Everything's its own individual piece. It's like a times b times c. I don't need rule derivatives, or excuse me, I don't need parentheses. And again, there's nothing to simplify there. You're done. Okay? You're done. There it is. So, we definitely have to know those rules. We definitely, and that's going to come as we go through it. And tomorrow I'm going to give you a PDF electronically. I'm going to show you where there's a PDF of all these rules. We're going to go through them and we're going to talk about them. Okay? And we'll have that. Now, there's one last one I wanted to show you here. which is this one here. Well, now, we already talked about this one, right? Before you would do this, you would want to write that as tangent all squared, because your outer function is that, right? So we would bring the 2 down in front, leave the tangent alone, and we tack on, what's the derivative of tangent? Anybody remember? Secant squared. The derivative of tangent is secant squared. Okay, last one, and again, we just have time to just mention it here. So then we could get into something like this, right? So we've got this mess cubed, right? So what's the outer function? The cube. So we're going to do that first, right? So we're going to bring the 3 down. We're going to leave the inside alone. So we're going to bring the 3 down. We're going to leave the inside alone, which is what the rule says to do. We're going to drop that to a 2. Don't forget that. A lot of times people forget that. Times, and man, am I going to put a big old set of parentheses here. Because now we're going to do the derivative of the inside, and what do we got there? We got a quotient rule, right? We got a big old quotient rule, and so we're going to have this big old thing there that we might have to do some simplifying to and so forth. We have a big old quotient rule there. All right? And maybe that'll simplify, maybe some things will happen, whatever. But that's where the chain rule is. And so there, on those last ones, we start to see where we can combine some of what we've had. Now, we went a long ways towards learning all of the new stuff we need for the gateway test, to be honest with you. There is one other little technique we have to talk about tomorrow, and we are going to throw in some rules on the arc, sine arc, cosine arc, tangent. But then that's it. I mean, and then a lot of it's going to be this stuff we've seen here already. So a lot of the rest of this week is doing those things, answering your questions, but then also practice. But with the shorter class periods, we lose a little bit of practice time for in class. Okay, we just do. Now, maybe your map testing is getting done early, so you can spend some time on it in there. I don't know. Certainly do not rush through your map testing so you can work on your calculus. I would never want you to do that. But, okay, no. But anyway, but the homework is a 3.2, okay, the 3.2 homework. But as we go through the week, we're going to have those website practice you can do, and it's really going to be, imperative, I think, to spend some time on there. Hopefully you've got some time this week. Some of you are really busy. I know a lot of stuff going on. But